Hello. Okay, everyone, I apologize. This is take 2 for me. And so you can see that, like, I messed up here. And so I want to talk through this. And so just follow along with me. I'm going to explain what I have here, and then we'll dive into mole percent. Okay. This topic, 1.4, has 2 parts to it. One is talking about percentages, whether it's mass percent or mole percent. And then the other one is a separation technique. Like when you have a mixture of 2 things, how do we know the best way to separate them? And so percentage broadly, let's start there. Like what even is a percentage? And a percentage is when you have a portion of a total and you take whatever that portion is and you divide it by the total. That would be like the fractional component of this. And then to turn that into a percentage, you would multiply it by 100. Okay? So, for example, let's say that I want to figure out the mass percent of carbon in carbon dioxide. So that would mean I need to know mass, grams, and I want the percentage of carbon. So this would be the grams of carbon divided by the grams total, which is our carbon dioxide, and to turn it into a percentage, I would multiply it by 100. Whenever you're doing a mass percent, it's really convenient to choose a sample that is 1 mole. Okay? And here's why it's so convenient. What if I have 1 mole of carbon dioxide? Well, what would the mass be of that total? And we go to our periodic table and we add together the molar mass for carbon plus the molar mass of oxygen twice. 12.01 plus 16 plus 16. And that would mean in this 1 mole sample, it is 44.01 grams of carbon dioxide. Great. Now we want to know of this total, what is the mass percent of only the carbon? Well, in this 44.01 grams, 12.01 grams of that total is carbon. Okay? So 12.01 grams divided by the total, and then timesing that by 100 turns it into a percentage. So we have, of the total carbon dioxide, 27.29% of that is carbon by mass. And we go, great. Now, our total is just consisting of 2 things, carbon and oxygen. And if 27.29% is the carbon, then the remaining percentage must be the oxygen. So instead of doing this all again for oxygen, we can just do 100 minus 27.29% to figure out what the percent is by mass for the oxygen within the sample. Lovely. Now, one more time, but let's try iron oxide. So I cut this box in half. Over here is going to be mass percent, and then over here is going to be mole percent. Okay. With mass percent, my convenient sample is, and so saying they didn't give you a percentage, you are solving for a percentage, a mass percentage. The convenient sample is 1 mole. So what if I have 1 mole of iron oxide? Well, that would mean that there's 71.85 grams of iron oxide in that 1 mole. Because again, what I did is I took the molar mass of iron and I added it to the molar mass of oxygen. So in this 1 mole sample of iron oxide, it would be 71.85 grams of iron oxide. Lovely. Now, what is the mass percent of iron? Well, of that 71.85, 55.85 grams of it is the iron. So you take the grams of the item, the portion of the total, and you divide it by the total. And again, if you just did that without multiplying it by 100, this would be a fractional component, right? It would be 0.77, that's the fractional component of iron within iron oxide according to to mass, by mass. But to turn that into a percentage, I multiply it by 100. And so that makes it so of this total, 77.73% of it is iron. And like we did before, if there's only two things like iron and oxygen, then the remainder of that percentage has to be the oxygen. Okay, lovely. When it comes to mole percentage, not mass percentage, mole percentage, you're always going to be given a starting point. Like for this, I didn't have to be given a starting point. I can just go right from this 1 mole sample and figure out my percentages. But when it comes to moles, they have to give you a starting point. They might give you these percentages as the starting point, or they might give you actual mass numbers as the starting point. And so they say, hey, in this iron oxide, we found that it's 77.73% iron. So we can go back to assuming that 100-gram sample, right? Because they started with the percentages. So I have 77.73 grams of our iron. And then the rest of this 100-gram sample is 22.27 grams of oxygen. Well, I don't want masses, I want moles because it's a mole percentage. So grams of iron to moles of iron, and grams of oxygen to moles of oxygen. And this was 55.85. All right, so if I take that 77.73 and I divide it by the 55.85, I will get 1.39 moles of iron. Okay, now what if I take the 22.27 and I divide that by 16? I also get 1.39 moles of oxygen. Interesting. Now this should make sense because look at this mole to mole ratio. There's 1 mole of iron and there's 1 mole of oxygen. So just like 1.39 moles of iron would give us 1.39 moles of oxygen. What if I want the percentage, the mole percentage of iron? Then I would take the moles of the iron, 1.39, and I would divide it by the moles total. And the total moles for iron oxide is the iron plus the oxygen, right? This 1.39 plus the 1.39. So 2.78, etc. moles. This is the iron. This is the total. Well, spoiler, you should get 0.5, and then when you times it by 100, then that's going to turn it into a 50%. Okay? That 50% of this iron oxide by mole, not by mass, is iron, and 50% of it, the remainder, is oxygen. And that's reflected in the formula. So this iron oxide, both of them have subscripts of 1. There's 1 mole of iron for every 1 mole of iron oxide. Okay. I want us to save these ones. We're going to do a couple of them in class. And those ones are specifically mass percentages. So reminder, if you're solving for mass percentage, it's convenient to have a 1 mole sample. All right, next. I like this problem, and the reason why is because look at how scary this looks. Like, we have all this information going on here, we got a graph going on here, and then at the very end, we got more data down here, and then the problem is the mass percent of CaCO3, okay? Look, I didn't read any of this. I didn't read this. I'm noticing that there's a graph and a data table, but I am always jumping right to the end, and I want to see what it's asking me. And what it's asking is, what is the mass percent of CaCO3? Okay, reminder, whenever we're doing a percentage, it's going to be the item that the percentage is about. So in this case, it's going to be the grams of CaCO3 divided by the grams total, this eggshell. And then to turn into a percentage, we'll multiply it by 100. That will give us our percent. Lovely. Now that I know what I'm going after, I need to figure out the grams of calcium carbonate, and I need to figure out the grams of this eggshell that contains the calcium carbonate. Once I have that, I'll be able to answer this question. So the next place I'm going to look is the data table. And the data table says, oh, look at that, mass of eggshell sample, 0.2 grams. It's right there, 0.2 grams. Okay, and then it says pressure prior to reaction and pressure at completion of reaction. And then now I'm looking at my graph. I always start with the axes, and it says pressure of gas produced and mass of CaCO3. So look at how much gas was produced. This was before the reaction, and then we had after the reaction. So we produced 0.070 atmospheres of gas. All right, so if we produced 0.07 atmospheres of gas, it looks like that was roughly 0.15 grams of Ca, 0.14, like it, or in between. It's kind of hard to tell. Let's do 0.145. We'll see how that goes. Grams of the CaCO3. All right, let's check. Let's see if this is even an answer option. So 0.145 divided by 0.2 gives us 72.5, but that's the fraction. Now I'm going to multiply it by 100 to turn it into a percentage, and we get 72.5%. Oh, look at that, 75%. There's some wiggle room for estimating there, but we got an answer that was really close. So it's closest to 75%. Nice. Now, we already talked about the difference between heterogeneous and homogeneous mixtures. And we have these three different processes, oh my goodness, of separating these mixtures. Whether it's heterogeneous or homogeneous, it doesn't matter. I have two things mixed together. And if we want to separate them, I could separate them through a filter. I could have them separate through a form of distillation or something called chromatography. Okay? Let's talk about filtration first. Filtration works really well when the items that are mixed have different sizes. When they're simply different sizes, or different states of matter. Okay, so filtration works great if the mixture is of two things that are different sizes, or if they are of different states of matter. Like the most common one is when a solid is mixed with a liquid, then I run it through a filter, and then that solid gets caught in the filter, and then I'm able to separate it that way. Okay? Distillation works the best when the items that are mixed have really different boiling points. So if you notice, like on a data table, and they say this thing is mixed with the other thing, and that in that data table you notice that the boiling points are quite different, then distillation is a great way of separating them. It's commonly done when the two items are both liquids. It doesn't have to be that, but like commonly they're both liquid and they have different boiling points. And then the last type of separation is chromatography. And chromatography works the best when the two things that we're trying to separate have different polarity of molecules. Meaning like one of the molecules is nonpolar and the other one is polar. Then chromatography is a great way of separating them. Okay. Okay, so I've seen a lot of questions, and they like look really scary, and you're saying, okay, you have this aqueous item and this aqueous item, and then you pour this other thing in there, and it makes a precipitate or a precipitate. Okay, I'm gonna make sure I get the spelling right. Okay, now a precipitate is in chemistry when you have two liquid looking things and you pour them together and it makes this like suspended solid, like it makes it gooey, slimy, or cloudy. Okay, and so if I have some kind of liquid or aqueous thing and I combine it with some other kind of aqueous or liquid thing, and then it produces some kind of solid, and then there could also be more aqueous or liquid, but I combine two aqueous things and one of the things becomes the suspended solid, then filtration is a great way of separating these, because we pour the product through a filter, and then all the liquid stuff, the aqueous and any water that's just floating around that didn't react, would go through the filter, but what gets caught in the filter is the solid. And just a reminder, when two aqueous things combine and they make a solid, that's called a precipitate or precipitate. So it is really nice to separate a precipitate from what it's mixed with through using a filter. The other type of separation technique is distillation. And this looks super fancy. Here's a simpler way that we could use this process. What if I have rubbing alcohol and it's mixed with water? And we need to separate the rubbing alcohol from the water. Rubbing alcohol has a way lower boiling point than water. Like it will boil at a much lower temperature than the water will. So if I put this mixture of the rubbing alcohol and the water on a hot plate or over a Bunsen burner, the alcohol is going to boil. It's going to go from a liquid state to a solid state much faster, way before the water will, right? We're going to hit its boiling point, and then that's going to become vapor, and then the water is going to be left over because we haven't reached its boiling point yet. So make sure that your temperature is at a temperature between the two boiling points, because you don't want both of them to become a vapor, or you don't want neither one to become a vapor. But this is a great way of separating two things that are liquid and have different boiling points. If we need to capture the liquid that's becoming vapor, that's where this distillation apparatus comes in, where here's the mixture, we heat it up, one of the two items, the one with the lower boiling point, boils, becomes a vapor, and then we can cool it back down and turn it back into a liquid, and then it separates the two. Okay. And then the last type of separation that we're going to talk about is chromatography. And with chromatography, we have more than one type of molecule mixed together, and their polarities are different. So really commonly what we see is that we'll have polar molecules and then non-polar molecules. So I'm going to grab a magnet. Hold on. All right, now my non-polar is going to be this. All righty, so imagine that I have this sample, and this sample contains some molecules that are polar and some that are non-polar, okay? And I'm going to place a bit of my sample on this piece of paper. And so those are the molecules that are non-polar. These are the molecules that are polar, okay? So it's kind of like, oh, can I scoot it over? Careful. It's this guy. I put the sample on the bottom of a piece of paper, okay? And then I'm going to have a liquid travel through the paper. And the most common liquid that we use, but it's not always this, is water. And water is also polar, okay? So what if I have this water and it travels through this paper, and the water travels through the paper? Well, what happened? It separated these polar molecules from these non-polar molecules. We call the water the mobile phase. And so if the mobile phase is polar, then whatever travels with it is also polar. If we switch it and the mobile phase, it's no longer water, it's some non-polar liquid, then whatever traveled with it would also be non-polar. Okay, so if the traveling liquid is polar, then whatever it pulls is also polar. If the traveling liquid is non-polar, then what traveled with it, pulled along with it, was non-polar. And so again, chromatography is a great way of separating polar and non-polar molecules. Alrighty. Shorter video, nice. So when we get to class on Friday, we're going to do a couple of these mass percent examples, and then we're going to remind ourselves about when we should be using a filter to separate, when we have a distillation technique that separates, and when chromatography would be the best way to separate things. And then I'm going to take you guys in, and you're going to do one of these kinds of paper chromatography separations. And so that's the plan for Friday. Okay, I'll see you all in class.